Hi guys, in this video I will be showing you two separate proofs that a random walk will always return to where it started. To be more specific, say I start at the number 1 on the number line, and each step I have a 50% chance of moving to the left and decreasing my position on the number line by 1, and a 50% chance of walking to the right and increasing my position on the number line by 1. Then the theorem that I'll be proving says that the probability that I have made it back to the origin after some number of steps in will approach 100% as n goes to infinity. This proof uses repeated symmetry in a really nice way. First, note that for any fixed whole number m, there is a 1 over 2 to the power of m chance that our next m steps will all be to the right, because each one has a 50% chance of being to the right, and we would have to get m of them in a row. So if we were never to return to the origin and we just kept walking forever, because we're doing this an infinite number of times, with probability 1 we would eventually have this occur and we would move to the right m steps in a row. So therefore, our position after we moved m steps to the right in a row would be at least m. So to restate what we have just shown, this means that if we never are to return to the origin, we will, with probability 1, reach a distance m for any fixed m that we choose. Now, let's mark all the powers of 2, which are 1, 2, 4, 8, 16, etc., in red, like this. Note that each red point is exactly halfway between the next red point and the origin. For example, 1 is right between 2 and the origin, 2 is between 4 and the origin, 4 is between 8 and the origin, etc. So, fixing some point 2 to the power of m for some m, by symmetry, any path to the next number is equally likely to take us back to the origin instead. For example, if the point we were at was 4, then to get to 8, we could go right, right, left, right, left, right, right, right. However, it is just as likely that we do the exact opposite path, which is left, left, right, left, right, left, 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 which would send us back to the origin. So, in general, this means that if we are at the point 2 to the power of m for some m, our probability of making it to 2 to the power of m plus 1 is 0.5. So therefore, from our initial point of 1, which is equal to 2 to the power of 0, we have a half chance of making it to the number 2. Then from there, we have a half chance of ever making it to the number 4, a half chance of making it to the number 8, etc. So we see that as we choose an arbitrarily large distance, the probability of us ever reaching there goes to 0, which means that we are guaranteed, well, with probability 1, to always stay below that point. But we already know that a path that goes on forever with probability 1 will go arbitrarily high. So that means with probability 1, our walk will terminate, which means that we will eventually go back to the origin. The second proof involves an interesting gambling argument. Let's assume for contradiction that there was a non-zero chance, call it c, that I would never reach 0. We know from earlier that this means with probability 1, we will reach n for any arbitrarily large n. Now, let's take n to be a number larger than 1 divided by c. So if c was 20% or 0.2, we could set n to be anything larger than 1 over 0.2, which is 5. Now, let's turn this random walk problem into a gambling simulation. Let's say that I had $1, and each turn I flip a coin. If it comes up heads, I win $1, and if it comes up tails, I lose $1. I'll keep playing until I either have no dollars left, so I have reached 0, or until I have n dollars. Now, let's compute the expected amount of money I will have at the end of the game. Well, there is at least a c chance that I will quit the game with n dollars, because we said there was a c chance that it would go on forever, and in that scenario, I am, with probability 1, going to at some point get to n dollars. And there is a 1 minus c chance that I will have no dollars left when I leave. It could be smaller, but this is basically the maximal possible chance that I do not go on forever, and hence that I can end up back at 0 and leave the game. So the expected value for the amount of money I leave with is c times n plus 1 minus c times 0, which is equal to c times n. And again, this is just a lower bound. It could be larger. There could be a higher chance that I do end up going to n. But we know it's at least c times n. And since n is greater than 1 over c, this means that c times n is greater than 1. Which means that, on average, I will walk away with over $1, which is more than I started with. However, by symmetry, it should be impossible to have the expected value of how much I make be anything except for 0. To see why the amount of money I make should be on average 0, note that each time I play around or flip a coin, my expected amount of money up to that point does not change, because there's a 50% chance I will make $1 and a 50% chance I will lose $1, and these will cancel out. To make this completely rigorous, you can draw a tree of all possibilities, and note that each time there's a branch split, the two halves of the tree will cancel out, and there will be no net change in expected value of the amount I'm making. So therefore, we have reached a contradiction, because we see in the scenario where I do this gambling strategy, I am on average making some money, which means that my expected value of the amount that I make is non-zero. And so therefore, our original assumption that there was a non-zero chance, C, that I would never return to the origin, must be false. And so we have proven the result. Thanks for watching.